Okay, so far we have defined the Lebesgue integral for it. We started with simple, with characteristic functions, simple functions. We moved to non-negative measurable functions, and now we are ready to kind of just close the gap and define the Lebesgue integrability for general measurable functions. Almost, we need one technical thing, but it's a very minor assumption. Okay, so say you have a measure space, like this is this one. We're going to define the set of integrable functions. It's L1 of mu, but set of integral functions. These are all the measurable functions, and measurable in where from x to r bar, right? As before, but without the plus. So these are all measurable functions. They don't have to be positive or non-negative, but you do require that the integral of the absolute value of f is finite. Put differently, just remember that if f is measurable, then also its absolute value is measurable. So put differently, what I'm asking is that the absolute value of f is integrable, right? Because it's a non-negative function, we define. Sorry, it has a finite integral. Good. So functions in this set are called mu integrable or just integrable. And intuitively, what the reason you require that is you don't want pluses and minuses to negate each other and cause weird stuff, right? So requiring that is really requiring that cannot happen. So more particularly, and also for defining the actual value of the integral, if you give me any function which is integrable, namely in this L1 of mu, you can always write it as f plus minus f minus, right? Where you understand what I'm saying by that. F plus is the kind of non-negative part, and f minus is the say negative part. Okay, so you can always, if you have a function, maybe it looks like that, then this is f plus, and this thing is the minus of a minus of f minus, right? So you can always write the function as f plus minus f minus. In this case, this is f plus, and this is minus of f minus. I just want f minus to be in s plus, right? To be non-negative. And this requirement really just says that both f plus and f minus have finite integrals. Note that both of them are in are measurable. It's an easy exercise. If it's measurable, both of them are measurable, and they have finite integrals. And we define in the natural way, of course, we define the integral of f with respect to the measure mu as the difference between the integral of f plus and the integral of f minus. And note again, there are no infinity minus infinity issues because this assumption essentially means that both of these are finite. Right? If one of them would have been infinite, or both, then this integral will also be infinite. Good. So some words about notation. It's sometimes convenient to refer to a variable, and sometimes doing that without noticing. So we have defined this thing, right? No, there are no variables, but sometimes it's useful to write that because technically because you don't write the function, you write the function value, right? So for example, when you write something like that in the usual plain old Riemann integral, we all understand that the function is the function that takes x to x squared because the way it's written, right? So it's sometimes you don't write this where f of x is x squared. You just put the function value rather than the function itself as the argument for the integral. So it's just a useful way of working, right? It's nice to work with variables. So we adapt this also in the Riemann integral, the Lebesgue integral setting, right? Things like that. So sometimes people write the integral of f of x d mu x, and some other people like to write the integral of fx mu of dx, which actually is I actually use that all the time, but this is makes a lot of sense because it's like the mu of the x, right? The measure of the little x. It's just a notation, but it makes a lot of sense. So you will see that sometimes. So keep that in mind. Another remark is that we did everything so far for real valued functions, but you get a complex value in integrability theory for free because you can just reduce it to the real setting. So for example, a function from x to c, where x is again some abstract measure space, and c is equipped with the corresponding Borel measure, which you would imagine what it is, if you want. You can define the integral like that. Right? The integral of the function, you just take the integral of the real value plus I, the integral of the imaginary part of the function, and you define this function to be integrable if both these functions are integrable, and you just inherit all the theory from the real valued setting. So you don't even have to worry about Borel the Borel measure of C. You can. It's very simple. It coincides with what happens when you do that. But you can always just reduce to the case of real valued integrals. We will work with complex valued integrals, so we will always do that. So that's what I said. A function is mu integrable if and only if it's both its real and imaginary parts are.